before I start, congratulations for a great initiative, and then looking forward to further collaboration in the future. So I would like to introduce work we're doing at MIT. The title is Robots for Physical Interaction. I'm going to show a bunch of Lego robots, but keep in mind it's all about physical interaction. So repeat the words as many as possible. Last 2 decades, we've been focusing on information technology. As you know, I can't believe there's only 10 years since, well, 11 years since the first iPhone. And I actually personally, I'm a little bit a conservative person. I don't think I need anything more from my cell phone. It's been only 10 years. You can imagine how much it developed. But you know, as you already previous speaker talked about how much computation evolved through last couple of decades, surprisingly, our electric motors and our magnets actually hasn't changed for the last 50 years. Our harmonic drive has a 40, 50 years of history. Hardware is slow. So if you think about providing a next level of service, physical services, you have to involve hardware. You need to involve physical energies. It's not going to happen just writing a software and then uploading in the app store and then somebody download it, right? You have to really think about how to deliver this energy, physical energy, and then happening in the hands of the customers. These are not going to happen that quickly, but it's going to be the main driver reshaping our life. You can think of any different thing: delivery, elderly care, companionship, farming, construction, home security, disaster response. None of these can be done without having actually a system that can provide the physical energy. And I want to point out that all of these physical services cannot be done without having mobility. So that's why we're focusing on mobility. But let's get on to the physical services. What are the physical services we have in our society? This is one of the screen capture from BMW i3 factory. Now it's a little bit more appropriate in Germany and not so much in Japan or US. But these are amazing robots. They are faster, more accurate, much more consistent than human, and they don't get tired. They're super accurate. They can do all these things really well. But if you really look carefully, none of these robots are actually dynamically interacting with the environment. So when it comes to soft object, even of cabling, all has to be done by human. Because none of these tasks that require physical interaction, dynamic physical interaction, cannot be done by just coding a position. All these robots are actually just following a predetermined trajectory. So when it comes to literally physical interaction, not just moving object from one to another, cannot be done by just writing a position. Antonio already showed this video, but I would like to show some clip from the DARPA Robotics Challenge, which is designed to tackle disaster response. But because there are amazing algorithms and amazing engineers working on it, but the software, the hardware is actually not quite well suited for this kind of task. Because many of these robots, not all of the robots, but many of the robots actually have a component came from manufacturing application. They're pretty much the same technology. But if you can see, if you look at the animal world, things are quite different. Biggest difference is these are built to handle impacts. Probably none of you think about this every day. I think about every time I walk. Every step is impact. Every time I grab my cell phone from table is impact. And then we are actually dealing with it. It's a visual for you because your hands are doing automatically. You are not really aware of what your hand is doing. Please think about during lunch, think about what your tongue is doing. You have to chop your food down, and then if you big piece come out, you have to push back to the teeth. Your teeth doesn't have any intelligence, right? You're chomping down. And then if pieces are small enough, you can throw into the back of the throat. And if you find a small piece of paper, you bring out your two lips while you're talking to your friend and talking about politics. And you have absolutely no idea what your tongue is doing. Same thing happens in your hands and everything. So my point here is really we need to think about how to change our paradigm, robot design paradigm from ground application where everything is known, position accuracy is actually guaranteeing success of the task. Where mobile application, nothing is really like that. Your robots are not anchored on the ground. You have to balance control. You have to control your balance rather than your position accuracy. Force control is way more important because nothing is certain. You always have to deal with uncertain environment. You have to deal with a situation where unexpected collisions all the time. So design paradigm need to really shift, and then many other people, even in this room, has worked on this area. I just want to point out that the conventional machines are typically stiff, and then with the stiff sensor, The series elastic has been really popular, and there are many success examples. In our group, we actually taking old idea and then come up with a different, slightly different concept. We call that perceptive actuation. We basically minimize inertia as friction between the actuator to the end effector by reducing gear reduction, reducing all the inertias, and then maximizing the torque density of the actuator. So we can actually get rid of a lot of system level, but we can actually maximize the force bandwidth. So I would like to show a couple of examples. The first one I would like to show is a Cheetah 2, which we published in 2014, I believe. And many people say that, wow, it looks like a dog running. But I want you to look at the machine that handle impact. This is non-trivial machine. This is about 30 kilogram, 32 kilogram robot running about 22 kilometers per hour. It's as fast as me. And every impact at the high speed, it occurs about 50 to 80 kilogram force in each foot. And I'll show you data. Those time on the ground is about 80 milliseconds. It can turn, is pretty terrible actually at turning. I'm going to show you a better machine later. And this is the first time we integrate the vision to react on an object, obstacle. So you can actually, the LiDAR system, look at the obstacle and then measure distance, measure the height, and then we run a real-time optimization. At 10 hertz, we actually solve this problem every 10 times in a second, and then react upon and then jump and land. So most important part in this video is actually landing. We spend about 95% time how to land. Jumping, recognizing object, solving was a piece of cake. Landing, not falling is actually the hardest thing. So this is video from 2010. We first build the leg and then see how much we can exploit the concept. So we can impose whatever impedance within the stability range. We can make it into a damper, pure damper now. We can make it into a spring. And we can change the millisecond level. It depends on situation. This is an impedance control example, but most of the time our robots are actually under force control situation. So in the swing, leg swinging is all impedance control, position control with the feedback linearization to make a position accuracy better. But as soon as hit the ground, we switch to the force control regime, and then all the inertia is ignored as soon as it hit the ground, because the body inertia basically dominate. This concept is actually not necessarily new, because Phantom, there are some examples, but best example I think is 1994. This is actually bigger main motivation, main idea source from for our Cheetah robot. So the Phantom is the best, in my opinion, the force display, haptic display device, and then the concept is exactly the same. Ken Salisbury never actually published a paper about this. So we actually made a bigger version, but it's a focus on force density, because the haptic devices tend to be very weak, can actually deliver high torque, and so we actually focus on motor design and then other aspects, so we can actually use it in the real system. So we call that Phantom and steroid. There are many advantages, but one of the biggest advantages, you can actually, you don't need to have a sensor in the foot. So we basically have a piece of rubber, but our robot actually can detect things without having force sensor. I'm going to show you many other examples later. Many people thought, oh, you're measuring currents. It's actually not measuring current. We're actually dominating the force. We're actually commanding force. We're detecting our deflection, and then deflection actually dominates how much force we're recurring. There's some noise issue, but majorly we're actually controlling forces. I don't want to go through all this math, but we realize what is most important aspect of actuator design is actually inertia. So we look at the inertia distribution, and then basically the best way to describe how backdrivable your system is actually inertia ratio. So we call that, like, don't call backdrivability anymore. We have better metric, which is IMF, impact mitigation factor, which is basically comparing your inertia matrix as the end effector compared with your worst case scenario. It's a locked position. So it doesn't work with the non-floating based machine, but you can always make the machine float and then apply this, and then you can calculate your IMF. That will be best representation of your machine's capability of handling impact. So this is the video I would like to show. Our machine is running, and then basically look at the data. The blue is the commanded control force. on the ground action force, and then red is actually measured. There's no feedback, you're just comparing the commanded and measured, and then there's pretty bad accuracies, like 15, 10%. But I want you to look at the time axis. This is about 80 milliseconds. 80 milliseconds is most manipulator people's accident. It's hitting like this. Your blinking eyes takes about 400 milliseconds. About a fifth of the time, we should be able to control ground action forces up to 50 to 100 kilogram. And then that's the level of force bandwidth we need to have to make robot runs and balance. And then why do you need to be that fast? That's all time you have. Real Cheetah is running on 60 mile per hour, 70 mile per hour. Each leg stay on the ground about 45 milliseconds. When you guys are running around and jogging around, each leg has about 150 milliseconds. When you're walking, you have a 400 milliseconds, but that's still very short period of time. If you cannot control that very short period of time, you will not be able to balance. So that's basically the nature of the locomotion. And if you think about manipulation as fast as human level, it's actually not that different. You have to think about the force bandwidth as one of the major criteria. I want to briefly talk about energy efficiency because I'm working on mobile robot. The y-axis is a cost of transport. It's a very common metric in the biomechanics community. That's why these are animal data. And as you can see, heavier animal, x-axis is mass. One is a 10 kilogram, two is 100 kilogram. Human is here. And obviously, heavier animals tend to be more efficient. Human is pretty efficient. Japanese robot, one of the best walking robot, has about 2. It's not as good as human. Cheetah is actually pretty good, even though sprinter. And the hydraulic machines are actually really bad in the efficiency because these are actually quite fast machines. Our machine is actually better than animal at this point. Well, we're not really proud of this because first of all, we're measuring efficiency using electricity. And then we actually didn't design to be efficient. We actually designed to be maximum high force bandwidth and happen to be efficient. But in my opinion, if you use electricity, if you use a battery, you should be much better than animal because it's not actually fair comparison. I just want to point out, like, by the time we were building the Cheetah robot, it was very controversial. A lot of people think it's not going to work. And after we showed the success, and then many people start kind of taking our concept. So spot mini Boston Dynamics, not all the joints are actually employing our concept, but the knee joint is the most important joint for handling impact. Actually take our concept and then use it. One of the Chinese company actually sort of copied the Boston Dynamics robot, but actually actuation concept is exactly the same as us. Cassie is another example. So many successful robots start taking over, start employing our perceptive actuation as a successful source usage of the case of the actuation. I want to introduce a third version, which is the latest version. And it's heavy, it's still 40 kilogram, and each joint can generate about 220 Newton meter, which is about as strong as a car engine, like sedan car. But you shouldn't be surprised. Most of your knee can actually generate about 200 Newton meter. So you can actually attach engine on your knee, and then your knee will win over engine. Your hip can generate about 300 Newton meter. So this robot is to start running at MPC, model predictive control, looking ahead about half second in the future. And we're writing a cost function around that state in the half second in the future. So it is good for dynamic maneuver because you need to really predict in the future. The instantaneous controller is really not good for this dynamic gate. And again, the machine is designed to handle impact. So those gates are just a part of the story. And then machines should be able to handle those impacts all the time because that's the nature of leg locomotion. The interesting thing about the leg robot is actually you can command the direction of motion and then orientation independently. So you can command turning left, 1 radians per second, and then going 45 degrees to the right. You can do that. Each leg has basically have a 3 degree freedom force source. And then ground action force control bandwidth is about 20 to 30 hertz, which is critical. You can command the same algorithm with the 3 leg, assuming 1 leg is broken. And this part is interesting. You don't use any prior information of the stairs or camera. These are all based on touch base. So as soon as our touch algorithm detect, oh, this is a contact, and then that become a ground, and then we create a new ground reference, and then we create our own desired position. These are all done automatically. So contact detection become very critical part of our algorithm. If you don't know how to switch from the swing to the ground, you can actually go over obstacle very, very well. One of the reasons why we're focusing on blind control is we don't want to rely on camera on every single detail on the ground. That's going to slow down and I think mitigate our robustness in the navigation. You might find this looks kind of weird because it's not like an animal, but this robot doesn't have any spine or whatsoever. And then if you look at it more than an hour, you realize that's actually the best way to jump up. And then many people, how are you going to jump down? This is how you jump down. It looks even more strange. But if you really think about minimizing pitch rate and minimizing pitch at the target, that's actually how you're supposed to jump down. Again, your brains are firing mirror neuron. That doesn't look like dog or cat because our robot doesn't have any spine. You know, the hardwares are difficult. It's fragile, low bandwidth. Torque is always not enough, and then dangerous. Any of you like work on hardware, you will agree with at least 3 or 4 of them. Difficult to model, expensive. I'd like to provide some solution for this. So we actually are building 10 of mini Cheetah. It's about 60% of the big Cheetah. And then that actually allows us to have a 9th or 8th of torque. That makes it inherently safe and then a lot more capable. So this robot actually negates all these 6 challenges in hardware research. It's very cheap and very robust and extremely high bandwidth and extremely powerful. And the model match really well. So they basically have all good characteristic of hardware we can test. Again, same perceptive actuation concept. I can't imagine any other actuation allowed to do this. And now we're not actually using custom motor. These are actually off-the-shelf commercial motors, so they're extremely cheap at this point. The only challenge is in this scale, the robots are smaller, your contact become a lot more uncertain, and the contact time is shorter as well. So we do that all the time. We do that like 10 times in a day. It doesn't really matter. It has a very simple state machine, so you can recover whatever posture, and then it doesn't break, as I said. And so we're building about 10 of them, and then 5 of them are going to be distributed to the academic institute. We haven't quite figured out the process yet, and then we're going to collaborate using this machine. So anybody want to try different kind of algorithm than us, if there's any common interest, this is going to be the ideal platform to test. So skip another backflip part. I want to spend a couple of minutes introducing basically future of our lab. We're focusing on more near autonomous mobility with the human manipulation. So we've been working on full body manipulation using human body, but this is more of we call it balance feedback. So we trying to utilize the human intuition on balancing the robot. But not necessarily we're trying to balance the robot, we're trying to actually be able to do power manipulation, like that takes a lot of forces. Because when it comes to mobile robot, we're not allowed to, it's very difficult to apply high forces on the environment because you have to balance yourself. So in order to do throwing axe or opening heavier door, you need to be able to utilize your body. So my student is actually working on synchronization algorithm. So there's a motion capture system with the force sensor on the ground, and then his algorithm automatically, independent from scale of the robot, he can actually synchronize the simple dynamics between the robot and the human. And the human is wearing this haptic feedback, so it is apply forces to match the dynamics. And when it comes to actual detail manipulation, we are also working on 6-degree freedom version of this. This is the same perceptive actuator, but it's set up in a bilateral teleoperation setup. So my hand actually can sense all the forces of the other robot, and then has extremely high bandwidth, and then impact mitigation without having the instability issue, unless there's a delay in the communication. So I just want you to think about in the future. This is one of the applications you can think of. But in this simple task, like moving a person from the bed to the chair, how many delicate contact has to be happen? I'm not sure humanoid is the right thing to go, but even in this task, human has to be very, very handled very gently. Very, very tricky situation. You can think of many other areas. The physical interaction is going to be a very important part of our robotics application in the future. Thank you very much for your attention.